introduction, and thank you all for joining today here in person and also online. And I'm going to talk about coordinating data centers with the power grid and to do that towards achieving sustainability in computing. So data center energy cost has been growing all over the world. This map shows a distribution of the density of data centers across the globe. Today, the total consumption of data center energy reaches nearly 500 terawatt hours globally. So this is clearly a gigantic number and constitutes about several % of the whole world's electricity use. So why is this the case? Because data centers have been at the backbone of almost any application we run today, from data analysis to user applications of all sorts, retail, entertainment, finance, healthcare, scientific research. So all of these rely on data centers in the back end. So Frontier is an example supercomputer, one of the top supercomputers in the United States right now. It consumes about 30 megawatts peak power. This is a modest data center, and it still spends about $40 million annually on electricity costs alone, excluding any other operational costs. So I said modest because when we look into hyperscaler data centers, we see hundreds of megawatt data centers, quite a few of them, in fact, today. So clearly, there's a lot of energy, a lot of cost associated with that as well. So this growth has been around for a while. We've been talking about data center electricity consumption growing for the last couple of decades, but there's been a recent surge, quite different than what we've seen before. This plot is from McKinsey, and it appeared in Washington Post earlier this year. It's predicting what kind of energy demand will come up in the data center due to AI. As we see here, this is in gigawatts. So as we see, there's a substantial increase projected for the next 5 to 6 years even. So going from 20 gigawatts range to 30 gigawatts. This is in the United States alone. So it's good to think about, like, each gigawatt means similar generation to the amount of power generated by a large-scale nuclear power plant. So we are talking about a difficult problem. It's clearly not easy to just add gigawatts of power into the grid to maintain this demand. Why is this demand? AI is becoming pervasive. Everybody uses ChatGPT or some sort of large language models in their applications these days. And if you do a ChatGPT query compared to a traditional Google search, you are consuming about 10 times more energy just by one average query. So I like this quote, computing is like potato chips, there's never enough. Even when we solve how to deal with one energy crisis, we always want to compute more. Today our cell phones are able to do similar capacity computation compared to supercomputers of 20 years ago. So it's safe to assume the specific numbers might change, but it's safe to assume demand is coming up. So there's going to be more compute demand regardless of what kind of efficient solutions we find. So as I'm based in the US, we look into United States electricity projections quite a bit. And so this plot is from Electric Power Research Institute, a nonprofit. It came out just a few months ago. And the blue line over there is showing the actual consumption, and you see an increase in the last couple of years already. And the right side of the graph is showing projections. Even the low business as usual scenario, this is called pre-ChatGPT. So before AI did the last explosive growth. So even in the more conservative case, business as usual case, data center consumption in the US will still reach nearly 5% of its overall energy consumption. And again, it's good to think about United States as a big country. 5% of its electricity consumption is equivalent to some smaller countries' total energy consumption. So, and in higher growth scenarios, this number is even growing further to 7%, 9%. So we are spending a lot of electricity. Why is this important? Maybe good to think about where this growth is most impactful. If we look into per state, we see that the overall data center growth hasn't been homogeneous at all. Some states, actually 15 states in the United States, host about 80% of all the data centers in the United States. So there's a lot of clustering. And this is Virginia, home to the data center alley. Currently, Virginia's electricity consumption, 25% of Virginia's electricity consumption is spent by data centers alone. So that's a huge number, and there's a lot of community pushback regarding that as well, because when 25% of the electricity is going into data centers, people started talking about it a lot more, of course. Why is this the case? One could think that, well, we can have a lot more distributed development of data centers. Virginia is where the government is, so there's a lot of institutes, defense sector and the like associated with that. But also it has the nation's one of the best internet connectivity. So data centers started to grow there, and that trend kind of continued. And it tells us basically that there's a lot of factors in where data centers grow. Internet connectivity is a big deal. Also land or real estate opportunities, energy pricing. So many factors come into play when companies, organizations, governments determine where to put their data centers. So again, why is this an issue? Because the grid is already strained. So when you have 25% or 10% or 15% of your electricity consumed by data centers, and when there's increasing demand, it's not easy to just add more generation. It's not certainly easy to add more transmission. It takes many years to expand the transmission network in the power grid. So as a result, there's a crisis, right? And this crisis grows because there's also worldwide decarbonization goals. We want to reduce the carbon generated by fossil fuel energy production. Here, this is from New York Times last year. The orange shades show clean power, nuclear, hydropower, wind and solar. And the gray colors in the diagram are representing oil, gas, and coal production. And the top figure is the axes are not aligned. So the US total energy amount over there is 4 million gigawatt hours, for instance. Whereas on the bottom, the axes are aligned. The European Union is getting close to 3 million gigawatt hours total. So it's just same graphs in two different scales. So what is the story here? There's a lot more growth across the world in green energy production. That's a good thing. So we are producing more energy through renewables. However, there's still a very substantial amount of coal energy or gas energy in use. These are still fossil fuels. And going back to our story, why is this a problem for the data centers story? When there is more demand, how are the power providers going to match that? If they want to match it with renewables, there is increased challenge. Renewables are volatile. The sun might shine today, maybe not so much tomorrow. The wind might blow today, maybe not so much tomorrow. So there's more volatility in energy production. To match that with increasing demand becomes a much more difficult problem where grid is already strained and having trouble balancing supply and demand. What happens when the grid cannot match supply and demand? In Texas, in the US, where extreme weather events occur more frequently, every summer at this point, regularly, there are blackouts. There is increased demand due to air conditioning and other use of electricity. Supply-demand match cannot be met, blackouts happen. So clearly, we don't want that. So when we look globally, this is showing growth in either green energy production or fossil fuel energy production. The green circles are showing where there's more growth. It's not showing the actual energy generation, it's showing the growth. And the orange or red circles are showing where there's more growth in still fossil fuel energy. So overall, there is more focus on decarbonization, but we have a long way to go, and decarbonization is not an easy problem, especially, like I mentioned, due to this supply-demand match problem in the absence of large-scale, green, cheap energy storage. So going back to the server side, so what we have accomplished over the last few decades as the computing and electronics communities is that we have made our hardware a lot more efficient than before. So this plot is from AMD. It was presented at last year IICEC, which is the top chip design conference. So it's logarithmic scale, but you can still spot a very clear saturation in this graph. So this graph is showing efficiency, how much performance we can get from our servers per watt we are spending. So how much work can be done with the 1 watt of power consumed? So this graph has been growing over the last couple of decades, thanks to technology scaling mainly. However, it's slowed down. So it's not easy to make chips more efficient by just scaling down the technology. So that era has ended. If you look at the GPU story, GPUs are really providing a lot of opportunities for certain types of workloads, such as AI workloads. So there's been a lot of growth. You might be aware of this due to NVIDIA's skyrocketing stock prices, for instance. So GPUs have made a big presence in the recent data center development due to their success with AI. And their efficiency for certain type of workloads is better than the servers. However, it's hard to look at these numbers and say energy efficiency is going to solve the sustainability problem, right? So we need maybe 10x, 100 times, 10 times, 100 times more efficiency for the equation to change. Now, this might happen, but it's not going to happen tomorrow, and it's going to require some time to design more efficient hardware that goes beyond the efficiency limits of today. So when we look into today's Moore's law, so Moore's law used to be basically the number of transistors in a chip doubles every roughly 2 years. And that we rode that trend for a while. Right now, we are looking into performance per watt, how much efficiency we get per power we are spending as the new Moore's law. To continue this efficiency trend, there's a lot of developments in the research and industry for looking into advanced integration, packaging, and AI accelerators. There's a lot of research, lots of small and big companies working on these. But like I said, it's going to take a little time. And another important point is that efficiency is not the same thing as sustainability. In fact, there's a paradox known as the Jevons paradox that says that efficiency sometimes hurts sustainability. If you make something super efficient, then sometimes we make a lot more of that, and we use it a lot more, so we hurt the sustainability curve. So efficiency is needed, dramatically more efficient hardware is needed, but it's not going to solve the sustainability problem alone. So what we've been arguing is that data center is part of an ecosystem. It's not a standalone entity. So if we only look into data center efficiency, data center hardware, data center cooling, we'll get some results, but we won't solve the problem. So in this ecosystem, on one side, there are users, and users have quality of service requirements. So what is that? So if you are a user running some application on a data center, you want a certain performance out of your data center. Without performance, there is no data center business. If the data center is not meeting my needs, I'll go to the next competitor data center. So performance is super important. We were talking to the Electric Power Research Agency. They were saying that performance has been always number one. Power used to be like number 5, 6 priority for data centers. Now power is also becoming number one because of this capacity issues that I mentioned earlier. And they said, in their words, actually, it became a number one problem, then it became a CEO level problem. So CEOs are talking about it. It's on CNN. It's on the news, basically. So power is also an important problem now. But performance is a really important metric to meet. And then the data center consumes IT power and cooling power, and data center also interacts with the power grid. It gets the power consumption from the power grid. And power grid is not a uniform structure. It provides a bunch of different energy markets, pricing mechanisms, demand response programs, and the like. And there are new carbon intensity measures coming up in some countries as well. So let's take a deeper dive into this grid. An electricity grid, as I mentioned before, balances power supply against demand. This is a difficult problem because we don't have cheap, large green energy storage available. There are batteries, sure, but it's not a trivial problem to store hundreds of megawatt hours of energy somewhere and then just use it later. So as a result, there's a lot of real-time optimization and control in the power grid. And to make this easier, there are programs called demand response, and this is established in a number of countries and in a number of states in the United States. The idea is that if the demand is very high, then the power provider tells to some demand response participants to reduce their power consumption. So, for instance, in summer months when there's extreme heat, everybody is turning on AC, or due to some other event, there's higher demand. The demand response participants can reduce their energy to help balance the supply and demand. And when this happens, the power provider offers incentives to the demand response participants. So if I'm agreeing to regulate my power consumption, then I get some money back. And in the data center scenario, this is also important because if we have data centers participating or more consumers in general participating in demand response, it also makes the grid's job easier in terms of integrating more renewables into generation. Renewables bring a lot more volatility than fossil fuel production. So like I was saying, wind and solar power fluctuate a lot more. So it requires a lot more planning, and demand response can absorb some of that volatility. So we can basically make our loads more flexible in the grid to allow for more renewable integration, and it's overall better peak management of demand. So here's an example from Australia. This is from the Australian Renewable Energy Agency. It's basically showing a step-by-step. It's kind of like a commercial. So it says step 1, energy users sign up voluntarily in demand response programs to reduce electricity consumption at times of peak demand. Step 2, electricity demand is high. There's a surge, for example, due to extreme weather. Step 3, users reduce their energy consumption. Step 4, reduced demand helps balance supply and demand in the grid. Step 5, users are paid for their reduced demand. So users get money out of this. In the US right now, there are companies that are kind of doing some sort of a brokerage between demand side participants and power providers. So I can go and subscribe my building, my company, my data center into these programs. And they help me basically participate in these demand response programs, and then they monetize the demand response back to the company. So data centers right now do this kind of demand response. However, they do in a limited capacity on how much they control their power. Mostly data centers participate today through their backup generation. There's backup diesel-based power generation, and using that they can do demand response. So what we claim is that data centers are well suited for to be demand response participants. What does that mean? Data centers are well suited to be flexible consumers on the grid. So why? Because they are huge power consumers. Some of them consume hundreds of megawatts. On average, it's still tens of megawatts typically. So that's one. The second thing is data centers have a lot more flexibility compared to many other societal users of electricity. Data centers can increase the speed they are running, decrease the speed they are running workloads. They can run fewer servers or more servers. They can do a lot of power control, whereas, for instance, lighting is a lot less easier to control. Or even AC. When it's really hot, people really want their AC on, right? So the flexibility in data center workloads is a lot more. But an important aspect, like I mentioned, is to how to keep users happy in this scenario. So if I have a data center, if I tell you, well, half the time I may not really operate, then probably you won't do your business with me, and you will go to a data center that has high availability, right? So this is the big problem, like how to do this while keeping the data center users happy. So that's what we've been looking at, how to design flexible computing policies with performance guarantees. So to be able to solve this problem, let's look into demand response in a little bit more detail. This is a specific example for demand response. Many different programs exist. So what happens is we look ahead and do some prediction of what kind of power we need for the next hour. We participate in the power market, bid and get a contract. And then in this particular program, there's a power regulation signal that's going to be changing every few seconds. There are other programs that are slower and, typically correspondingly less valuable, but there are many demand response programs. So when I do this, and if I'm able to regulate up and down some amount, for instance, I'm going to say in the next hour my data center is going to consume 10 megawatt average that's needed to satisfy my performance, and then I can regulate plus and minus 2 megawatts. I'm going to be paying for that 10 megawatt and get reimbursed for the regulation amount of 2 megawatt back. So this signal is from the New York ISO, Independent Service Operator, that serves the New York area, power grid. And so the target power is given. It has some stochastic properties. We don't know the exact signal. And then if we follow it within some accuracy margin, it doesn't have to be perfect, we can participate in this particular demand response program. This one is called Regulation Service Reserves. It's part of the ancillary services offered in New York area. Similar programs exist in other countries and other states. Other examples of demand response, Google last year announced demand response pilots in Europe where they shifted non-urgent workloads to reduce power when needed. So basically they are delaying some of their workloads to run later. Lawrence Livermore Labs in the US hosts a supercomputer, and they agreed to their power providers to provide 8 megawatts of demand flexibility during a heat wave. So these are, you can find other examples. I think these are pretty interesting examples that are happening already. So when we look into data center demand response, there's a lot of different things. There are price programs coming up. I won't talk about that too much, but some people are working on the pricing mechanisms to make this energy market more attractive. We've been looking into incentive programs quite a bit, ancillary services, capacity markets, and participating in demand response has value. The value changes typically, as a rule of thumb, if you can regulate more frequently at a finer granularity, you get more benefits out of it monetary-wise. And there's also emergency demand response. This is basically when the grid says that, you know, I can't deal with this demand, reduce 2 megawatts, and if you participate in an emergency demand response program like that, you also get monetary benefits. And on the bottom, in this taxonomy, there's a bunch of different ways you can control demand response. In data centers, you can do power capping, scheduling, hardware or software power capping. You can shed some of the load. You can basically forecast and adapt your workload operation, and so on and so forth. So compute power has a lot of inherent flexibility. If I'm going to follow a power target with my data center, I can change the speed of my servers. The hardware is already equipped to do that. Let it be CPU or GPU. I can change the number of servers I'm using, so I can put some of them in sleep mode. Or I can change how many jobs I'm running at a time and maybe suspend some of the jobs to run later. And there are some other controls. This is not even comprehensive. So there's a lot of control mechanisms that let me, in a data center scale, regulate my power consumption at second level. So you can also do it at minutes and hours, but even at second level, you can regulate it accurately. So we've been designing solutions in my team to have a software suite, basically, for both forecasting and bidding in power markets, how to estimate my load for the data center so that I can provide performance guarantees, and also to implement runtime power regulation policies in data centers. So I'm going to talk a little bit about this. An important ingredient in providing performance guarantees is to express them in terms of statistical constraints. So without getting into deep math, just the idea, so how can I provide performance guarantee? I can actually express my quality of service constraints to consumers per different job type as a probabilistic measure, and I can guarantee, for instance, 90% of the time, this job type is going to meet its quality of service threshold. And this threshold is defined as a metric for how fast it can run without any interruption, without any slowdown. And then, for instance, I can say normally this workload takes 5 minutes. I'm okay if it runs within 10 minutes. So that would be my quality of service threshold. And I can tune all of these knobs. So I can say that, you know, this workload is super urgent. I don't want any delay on it. For another one, I can put more delay. I can change the 90% number as well. I can say I want 95 or 99% of my workload to meet their quality of service threshold, or I can make it more flexible. Typically, as we increase flexibility, we have more room for doing regulation. If all the performance constraints are super tight, then the amount of regulation is still there, but you know, the amount of regulation capacity I have drops. So our secret sauce to making this happen is to first run algorithms to do parameter selection for how much average power do I need to meet these statistical quality of service constraints. Do I need 10 megawatts? Do I need 15? How much regulation can I provide? Can I provide just 1 megawatt or 5 megawatts of regulation capacity? Because this is going to be the flexible capacity I offer to the grid. First, we run optimization methods for that. And then at runtime, we use combined knobs of scheduling and power capping on servers to make this happen. If I have a power target of 9 megawatts, I can meet that at second granularity. Next second, or next 5 seconds, let's say I have 9.1 megawatts, I can change my power consumption as needed. So I won't go into details of this, but this is basically our secret sauce. And we show this theoretically how we can guarantee workload performance We showed it in simulation, and then we designed a prototype. And for the prototype, we used Massachusetts Green High Performance Computing Center. We didn't use the entire data center. Unfortunately, nobody yet has given us a full data center to play with. But we are able to get some clusters in a data center to do prototyping. And we implemented all the power control necessary to control the power and ran a whole bunch of workloads on this. And we have an efficient, scalable software architecture that basically a primary node gets all the information, distributes it into client nodes, different power caps, and this is all implemented in hardware and software control. So, and then we started running things. This is before demand response. We are just sending some workloads to this cluster, and it's running. It's showing number of jobs submitted and the power consumption when we don't do any regulation, and then the different servers that are and their occupancy rate. When we do demand response, what we want is to follow a power target closely. And when we do that, we see that our cluster actually is able to meet that target very closely. So this was very exciting for us. And like I mentioned, we also provided analysis on workload guarantees and all of that. And when we look across different experiments, we tested tighter quality of service, looser quality of service, higher power applications, lower power applications, mix of these, and a bunch of different scenarios. But overall, it was very promising. We achieved between 30 to 50% flexible reserves provided to the grid in these experiments. So what does that mean? If I'm consuming on average 10 megawatts, then I can give 3 to 5 megawatts back as flexible reserves to the grid. That's a very substantial number. And actually, the incentive for doing this is also very strong for data centers. So they can potentially get 30 to 50% back. There's some non-ideal situations that always happen in real world. So sometimes, like in this case, you might have too much things to run, and then your power target is going very low. Or maybe you don't have enough workloads to run. Your power target, the red one, is going high. For these situations, we designed some add-ons to our policy for job preemption and then standby queue. Standby queue is basically having some extra jobs in case you are in the situation on the right that your power target is high and you can't meet it. You can get some jobs from the standby queue. Amazon has a spot pricing mechanism that's pretty similar to the idea of standby queue right now. You can pay only a small fraction of what you normally pay to Amazon if you accept that sometimes your workloads can be substantially delayed or sometimes they can be dropped. So if you accept that, then you can pay a lot less. So standby queue is kind of like that. You have some jobs, they will run eventually, you are not concerned about their performance. So power and performance challenges are visible at multiple scopes in a data center. So far, what I talked about was mostly related to jobs and clusters and the hardware and the software, how to control it. In a data center site, there is also non-IT power. In fact, on average, this was a study in 22 in the US, 35% of the power consumption is going into non-IT power, and a majority of that is cooling the data centers. So how do we do demand response when now we have this information that 35% is going into cooling? This is from the April report again, the recent April report. This is average annual power use efficiency. Power use efficiency is a metric that shows how much of the data center power is going into IT versus other non-IT things. So ideally, we want PUE to be 1. For an ideal case, if all the power is going into servers and network switches, etc., then my PUE would be 1. This used to be 2, 2.5, as you see in the graph. There's this tremendous drop over the last decade or 15 years. And now the average PUE in the US is about 1.5. And for more efficient data centers, this comes down to 1.2 even. So this is a great development, but this happened through integrating more water or liquid cooling in data centers. And that creates some other sustainability challenges that I don't have time to get into today. But basically, because data centers, some of these data centers are consuming large amount of fresh water, pulling water from freshwater sources, there is pushback in some communities because they are not convinced that the water should be going to data centers, right? So there are other sustainability issues with this much water use, but overall that was a gain in terms of getting much better cooling efficiency in data centers. Now, where do we go from here? Now, if I have compute power flexibility, on top of that I have cooling, which is typically have larger time constants, is a lot less flexible, but there's some flexibility there too. How do I do demand response with this entity together? So we designed this 3-layer software. The first layer talks to the grid operator. This is the data center side software. It basically talks to the grid operator in the sense that this is my workload. It bids for the hour-ahead program, gets into a contract. And then the 3-layer software is basically distributing available power to different jobs. There's a power modeler that looks into job-level power model as well as the data center cooling power model. And then there's an agent to implement it on the hardware. We implemented this version together with folks at Intel. GOPM is Intel's project, essentially, to control power in high-performance computing servers. And we have our own software that's integrated, that's open source, actually, at this point, to do this kind of power control while maximizing performance. So how do we get the cooling power in there? This is PUE data from Massachusetts Green High Performance Computing Center. There are 2 distinct regions in this graph that you can see. In Boston, Massachusetts Green High Performance Computing Center is outside Boston, a couple of hours driving distance. So we have cold winters, so about half the time they can just use external air without turning on the chillers for their water cooling. And then the right side of the graph sees this ramp up. As the temperature is hotter, then they have to turn on the chillers, so you have these 2 distinct regions. So you can derive this type of information from data centers today and prepare a data-driven model to optimize cooling along with the compute. And that's what we did. Basically, we have this policy that I showed before. We have a cluster simulator, and then we put the data center site-level power model on top of that and to do demand response altogether. So all of this goes into a framework that we now call FlexDC for flexible data centers. And flexible data center framework includes bidding and planning for the data center, flexible computing with performance guarantees. This is a very important piece to provide performance guarantees. And then scalable implementation all the way into the hardware controls. And the important thing is we are not changing anything in the hardware. We are using existing utilities that are available in the operating systems and cluster managers. And while I talked about demand response today, and the reason for that was because there are established programs for demand response. It's happening today already. These programs are available. So I talked about a specific program, and it's not just in the US, it also exists in Europe, Australia, China, and I believe Turkey is also looking into demand response markets as an option. Other options are possible. For instance, green data centers with on-site generation will be prone to these type of fluctuations, so you can implement FlexDC type of policies to absorb that volatility. There are some markets that are being tried for carbon-aware metrics, basically not just showing the electricity availability, but showing the carbon quality of that electricity. So you can similarly do a flexible operation in your data center following a carbon signal. So overall, FlexDC framework brings the ability to follow a power regulation signal, more aggressive, more ambitious, or less ambitious, depends on the specific program. What I didn't talk about today was data center collaboration that brings additional opportunities. And this collaboration could be happening across data centers of a same company. A lot of companies have multiple, or organizations have multiple data centers, so they have the ability to share workload. If there's high demand in one location, maybe more workload can be run in another location. There are, of course, some performance costs associated with this, but it's possible. It's actually even more interesting to think about a collaborative case where data centers of different companies, different entities are part of the same power network, and they can collaborate by sharing aggregate information without violating their privacy and business concerns and get better deals, provide more flexibility to the grid. And one of our projects is right now working on that, basically making data centers collaborate. So myth or reality? Hopefully you found it a convincing story that flexible operation is possible. It's actually possible today, And the immediate low-hanging fruit, immediate opportunities are, in my opinion, are in batch loads, basically workloads that run for a while on data centers. And there's a ton of them, high-performance computing, simulators of all sorts, and AI. A lot of the AI training loads fall into this category. And this can be implemented today with performance guarantees without hurting any business concerns. Collaboration is the next step to improve beyond flexible computing, to have data centers talk to each other and talk to a power provider to optimize jointly and provide even further capacity. Imagine in areas like Virginia, where 25% of the electricity is going into data centers, collaboration among data centers is going to make a big difference in how much capacity can be provided. And further down the line, the vision, I think, should be to optimize with load aggregators, data centers, and other consumers together in the grid. There are other growing electricity consumers, such as electrical vehicles and others, and some industry is also using increasingly electricity. So we can look into these problems all together and create a more sustainable framework. Now, I showed this diagram before from New York Times, showing the growth of energy, and Turkey still has growing coal or fuel-based, generally, energy. And this is from Amber, a think tank focused on climate. And in Turkey, and there are experts here who know a lot more about this, but coal and gas energy production has been growing over the last few years to meet the demand. Wind and solar are also growing. But again, based on the same analysis, there is tremendous opportunities, untapped opportunities in Turkey. As a comparison point, this report shows Turkey's solar energy, only 6% of Turkey's energy generation is coming from solar. And it says Poland, which is probably a lot less sunny country, also has 7% of its generation coming from solar. Greece has close to 20% of its generation coming from solar. So the target for Turkey to reach for renewables is 47% of generation by 2030. Whereas the International Energy Agency is giving a minimum target of 60%. So 60%, Turkey's target is right now below that, and there's quite a way to meet that target even with the current trends. So why am I mentioning this? There's also a growth in data center markets in the US. I think there's a lot of opportunities to think of these things together, because like I mentioned earlier in the talk, if we convert data centers into flexible loads, as opposed to typical power consumers, then there's opportunity to integrate more renewables, to make overall grid management easier and serve other growth in the grid as needed. And this could be through demand response mechanisms, but also could be through data centers having on-site generation of electricity. Thank you for listening. I appreciate everybody attending. Thank you so much.